In this video, we're going to talk about linear combinations. We're going to apply vector operations to write vectors as a linear combination, a single vector as a linear combination of more than one vector. So by definition, what a linear combination of column vectors are is that you have a certain number of vectors, you multiply them by scalars, and you add them together, and you will get another vector based on the scalar multiplied by the vector. Of course, all the vectors have to be the same size. Suppose we have an alpha, which is our scalar, and we're going to call it 3, and the other one -1. And we have the vectors v and u is defined by 6, 4, and 1, and also 1, 7, and 2. If I take my alpha, which was 3, multiplied by my vector v, and my alpha, which was -1, multiplied by my vector u, then it would look like this, 3, and then I'd make sure that when I do my vector operations, just like I learned in the previous video, it would be 3 times the 6, 3 times the 4, and 3 times the 1, minus 1, 7, and 12 in all the right places. So 18 minus 1 is 17, 12 minus 7 is 5, and of course 3 minus 2 is 1. Computationally, a linear combination is pretty straightforward. Now let's look at our equations that we had from our vector operations in our last video. We had these systems of linear equations. It was x1, x2, and then -5x3 is equal to 4. So this was the numbers or the equations that we had in our previous video. We can write them just like we did before in column vectors. So if you remember from our last video, we wrote these as the column vectors. The first column vector as x1 plus x2 minus 5x3. And then, so basically I took all of the coefficients and the variables and put them in a single vector. And of course, I put the constants in an additional vector on the other side of the equal sign. I can write this in terms of each x sub 1, x sub 2, and x sub 3. So I can take this vector and break it apart into 3 vectors. In my x sub 1 vector, there was one coefficient on the first 1, 1 position. There is no x sub 1 here, so that's why there's a 0 there as a placeholder. And of course, there's the coefficient of x sub 1 on this one. Going on to x sub 2, this has a coefficient of 1, 2, and -3, so 1, 2, and -3. And then of course, when we go to x sub 3, -5, -1, 2. So -5, -1, 2, and of course it equals the constants. So let's take a look at our first theorem. Our theorem says, I can take a linear system and write the solution as a linear combination. So if we have a columns of an n by n matrix, so we have the columns of an n by n matrix, we can denote them as vectors a1, a2, a3, just like here, a1, a2, a3. Then my x vector, which is of course the solutions, is elements of all the entries in that x vector are elements of the complex, whatever size we're looking at. And of course, we usually talk about R2 or R3, but it could be any complex Rm, is the solutions to the equations of the linear systems, A, B. So X is the solutions, if and only if B equals the linear combinations of the columns of A, of the matrix A, formed by the entries of X, being x sub 1 times the A, and then x sub 2 times the next A, the x sub 3 times the next A, and etc. And the proof, of course, is in your book for your viewing pleasure. Basically, what it says is that we can write the solutions of a linear system of equations as vectors, as a multiplier, alpha multiplied by the vectors that are formed by the solution. So once again, if we go back to our example that we had, we of course started out with the x sub 1 plus x sub 2 minus x sub 5. I'm not going to read them. We wrote them as column vectors. So we took them and we wrote them as column vectors. Now if we take the augmented matrix that is formed, and remember the augmented matrix of course would have been 1, 1, -5, and 4, 0, 2, -1 and 4, 1, -3, 2, and 1. Here's my augmented matrix. If I take my augmented matrix and I write it in reduced row echelon form, then that's the result. because a coefficient matrix is an identity matrix, right here, we know that the only solution to the system is when x sub 1 is 6.5, x sub 2 is 2.5, and x sub 3 is 1. The next theorem we get is the theorem of vector form for solutions of linear equations. So suppose that we have this augmented matrix, that's the notation for augmented matrix, is a consistent linear system. That means we don't have to worry about having a no solution, a linear system of matrix A, the coefficient matrix, and B, the vector, which is the constants, of M equations in N variables. Remember, these don't have to be the same. If B is a row equivalent M by N plus 1 matrix in reduced row echelon form. Suppose that B has R pivots, and the indices for those are D1, D2, all the way to D sub R. Then, while the N minus R non-pivot columns have indices of the free, these are my free variables, F1 to F of N plus 1. Defined vector C, and of course vector U, then we end up with a set of solutions to the linear system as C, the constant, and then the constant vector, that should have been bold, the constant vector plus my alpha, my first column vector, my second alpha, my second column vector. So what does this mean? Well, this means that the result of this theorem tells us the values of the free variables are the x sub whatever it is for the free variable. So if I take this system of linear equations, put it as an augmented matrix, and then I do it in the row echelon form, the reduced row echelon form, I'm going to have 1, 2, 3 pivots. That's my R. My N is 5. I have 5 variables. So I know that I have column 3, column 5 are where my dependent or basic variables are. And then column 2 and column 4 are my free variables, because those are the columns that don't have pivots. So what we end up with is the constants. So I write my equations where x sub 1, and it comes from this very first row, x sub 1 is 1, that comes from this constant, and then I'm going to move this x sub 2 to the other side of the equal sign, and then plus 6, and that should be a minus 6, actually, that should be a minus 6, let me make that minus 6, x sub 4. So x sub 1 has a constant, and then it has an x sub 2 and an x sub 4 variable in the free variables. Of course, we know that x sub 2 equals x sub 2 because it's the free variable. X sub 3, which is, again, my basic or dependent variable, and it's where the pivot is going to be 3. That comes from this constant. Remember, this is an augmented matrix, and if it makes it easier, I'm going to put that line there to show it's an augmented matrix. The constant, then plus 4, x sub 4, because I've taken this and moved it to the other side of the equal sign. So my x sub 3 will have a constant, and it'll also have a 4 as a coefficient on the x sub 4. X sub 4 is, again, the other free variable, so it is in terms of itself. So x sub 2 is in terms of itself, and x sub 4 is in terms of itself. And then, of course, x sub 5 actually is a constant. It is negative 5. So the way that we're going to write this is we're going to write first the column vector that is all the constants. If these are all zeros, like in a homogeneous system, you wouldn't bother writing this part of the solution. Now, what I know is that the only 2 places that I see in x sub 2 is in my x sub 1, so that's there. So the first position in all of the vectors is the x sub 1 coefficients or constants that we see as coefficients or constants when I solved for x sub 1. Let me put it that way. So then my x sub 2 would be in the second row. There is no constant for x sub 2 because it's in terms of itself. X sub 2 is in terms of itself, so that's why the 1. And then, of course, x sub 2 is in terms of itself. That's why there's no x sub 4. Going on to the x sub 3. X sub 3 has this constant. There's the constant. It has no x sub 2 in that solution part of x sub 3, but it does have a positive 4 in that. Oh, and that should be a negative 6. And I digress, sorry. And the x sub 3 has an x sub 4 in the solution of x sub 3, and so there's the 4 right there. Then I'm going to do my x sub 4. There is, for x sub 4, there's no constant, there's no x sub 2, but x sub 4 is in terms of itself. Lastly, that when I go to x sub 5, it only has a constant and it has no other free variables, so there's no coefficients of the free variables. So there is my solution in terms of some here and here, some coefficient that is a scalar. Because of the fact that this system is consistent, but there's an infinite number of solutions, then we know that I can have any x sub 1 and any x sub 2 and any x sub 4. Any x sub 2 I choose and any x sub 4, as long as I remember that it's a scalar and I multiply it into that vector, will be solutions to this system of equations based on the theorem up above. Okay, so let's look at the next theorem. The theorem now is going to be on the homogeneous solutions. Now these are the more specialized. The homogeneous solutions, say we end up with a coefficient matrix because it's homogeneous, we don't put the augmentation on there. So here's my homogeneous. I have the variables x1, x2, x3, x4, and x5. I put this into reduced row echelon form. I have a pivot in the first column, the second column, the third column, the fourth column. So that tells me that those are all my dependents. So my D is the first column, the second column, the third column, and the fourth column. My free variables only happens in the fifth column. So here is my free variable, and that happens in column number 5. So when I do the solutions, oh, and also just a reminder, my R, the number of pivots, is 4. The number of unknowns I have is 5, so we know we have one free variable. It happens in this column, the x sub 5 column, so that's our free variable. That means all of my solutions will be in terms of the f in the x sub 5. So when I take and write each one of these rows here, that would have been x sub 1 plus x sub 5 is equal to 0. So of course, that's why it is x sub 1 in the first position. Going down the x sub 2 in terms of x sub 5, x sub 3 in terms of x sub 5, x sub 4 in terms of x sub 5, and of course, x sub 5 in x sub 5. So our solution is x sub 5, and then it's -1, 4, -2, 1, 2, or excuse me, 1. And this is also, we know from our last video, and the video prior to that, this is the null space of our matrix A. What that means then is if I take and write all of these original columns, here's column 1, so here's column 1, and then column 2, and column 2, and column 3, and column 3, and etc. If I take each one of these numbers and multiply it as a multiplier for each column. So then here's my 4, column 2, my -2, column 3, my 1, column 1, column 4, and then of course going back 1 and column 5. If I do those multipliers, those scalar multiplications, and I multiply them by each one of those positions within the vector and add up all the positions, I'm going to get this homogeneous solution. I'm going to get the zeros, the zero vector. So as we take a look at this, we look at this example, can W be written as a linear combination of the 4 vectors? What we are trying to solve then is we are trying to ask ourselves, can we do some alpha, we'll call it alpha sub 1, 2, 4, -3, 1, 2, and 9, plus alpha sub 2, in the 6, 3, 0, -2, 1, 4, plus the alpha sub 3, negative 5, 2, 1, 1, negative 3, and 0. And then, of course, my last one, alpha sub 4, which gives me 3, 2, negative 5, 7, 1, and 3. Does this equal, can I get this to equal the 13, 15, 5, negative 17, 2, and 25? And if you're screaming in your head, yes, I can do that with writing the left-hand side as a matrix because of the theorems that we just learned, and then augmenting on my W, and then do the row echelon form and solve, you would be correct. And that's exactly how you're going to do this, is you are going to go ahead and you're going to write this as a matrix. Let me see if it'll show up on the black. Oh, it does. Look at that. So I would have 2, 4, negative 3, 1, and I get all excited to put the bottom part of the matrix in there, and I get ahead of myself. 2 and 9, and then I would have the 6, 3, 0, negative 2, 1, and 4, negative 5, 2, 1, 1, negative 3, 0, 3, 2, negative 5, 7, 1, and 3, and then of course I'm going to augment on with the 13, 15, 5, negative 17, 2, and 25. And now what I'm going to do is I'm going to go ahead and put that in my calculator. And if you're saying, wait a minute, you said we can't use that. Well, you are correct. I would not give you something like this necessarily on the test. I'd give you something much smaller, or I'd give it to you already in reduced row echelon. And I always want to put that negative there, or the bottom part. So let me grab my calculator and put this into reduced row echelon form. All right, so I got my calculator out. Actually, my calculator said it didn't like me. So I went out actually in a symbol lab, and this is what it reduced row echelon form turned into. We had 1, 0, 0, and then all the rest of these were zeros. We had a 0, 1, 0, and all the rest were zeros. We had a 0, 0, 1, and then a 0, the rest are zeros. And then we had 0, 0, 0, 1, the rest were zeros. And then on the other side, the augmented part was 0, 0, 0, 0, 1. So this is what it in reduced row echelon form. Now, this here tells me that it is a no solution. So that tells me that there is no way I can get a linear combination of these vectors here to add up or subtract up to become these numbers in this vector here. So the answer is no. And I was able to do that. I put it into the matrices, and that's based on the fact that the theorems up above allowed me to do that. So that's it for this video.